So today we are going to talk about the foundations of convolutional neural networks. In the last class, we have talked about uh, the classification and learning with convolutional neural networks. We have talked about different types of features which are detected across the different layers in the neural network. And today we will see the different layers which are found in the convolutional neural networks. So the objectives of the convolutional neural networks to understand the convolutional operation. So here we will understand the convolution operation in convolutional neural network. We will understand the pooling operation, and we will understand the different vocabulary that are being used in convolutional neural networks, like padding, stride, filter. And then we will talk about an application of convolutional neural network model. So if we see the building blocks of a convolutional neural network, then this is a typical convolutional neural network architecture. So in this architecture, we can see that there are a number of pooling layers, number of convolutional layers, number of pooling layers, and after the end of the convolutional layers and pooling layer, we have a flattened layer, and the flattened layer represent a one-dimensional feature vector, and this one-dimensional feature vector is fed to the fully connected layer, and in this fully connected layer generates the output. So this convolutional layer and pooling layer constitute the feature extraction. That means this portion represent the feature extraction part, and this fully connected layer separately represent the fully connected layer, or we can say the predictor or classifier. So through convolution and pooling operations, we can generate the feature maps. So after every convolution operation and pooling operation, so we generate the feature maps. So in this architecture of convolutional neural network, we have three main components. One is the convolutional layer, another is the pooling layer, and finally we have the fully connected layer. So this is a typical architecture of convolutional neural network. Now, if we look at the properties of convolutional neural network, then we have three different properties that are prominent in convolutional neural network: local receptive fields, shared weights, and spatial subsampling. So when we dealt with the simple neural network or general neural networks, apart from convolutional neural network, so we saw that there the spatial sampling or special images are not used. Instead, they have been decomposed into a number of neurons, and these neurons carry the information further in the next layer by summation and activation of the input information. But here, the convolutional neural networks have the characteristics that can enable the invariance to the affine transformation of input images that are fed through the network. Okay, so since the convolutional neural networks are having convolutional layers and pooling layers, so through these layers, the convolutional neural networks will enable the invariant property to the affine transformation of the images. Through affine transformation, we can keep intact the points, straight lines, and the planes of the input images when they are fed to the network, and this will provide the ability to recognize the patterns Now, sometimes the patterns are found to be shifted, tilted, slightly warped within images. That means if there are some deformations which are found in the input image, then those deformations or those type of patterns can be easily dealt with by convolutional neural network, because when convolutional neural network process an input image, the affine transformation is found as the invariant property of the input image, and through this invariant property uh, property of the input image, we can preserve the points, straight lines, and planes of the input image, despite having the deformation present in the input images. Now, convolutional neural network has the three main properties: local receptive fields, shared weights, and spatial subsampling. Now, what is local receptive field? Now, the local receptive fields are defined portion of a sensory space or spatial construct. So, a sensory space is nothing but the input image, or spatial construct is also represent the input image, and this receptive field which are defined in the image will contain the units that provide the input to a set of units within the corresponding layer. Okay. So if we consider receptive field is a 1 by 1 or 2 by 2 or 3 by 3 neighborhood area, so that to be defined in the input image, then that receptive field can use the pixel values or gray level values within that neighborhood area, whether it is 3 by 3, whether it is 2 by 2, whether it is 4 by 4, whether it is 5 by 5. Then these pixel values of the gray level values, which are found in the receptive field as in the neighborhood area of the input image, so they are mapped to the single unit in the next feature map. That means when the convolutional layer generates a feature map through convolution operation through a filter, then this receptive field, the number of points or number of gray level values which are found in the neighborhood area of the receptive field in the input image, so all those points are mapped to a single point in the feature map, which is found after the convolution operation or the pooling operation. So the importance of receptive field is to contain the units of the pixel values that provide the input to the set of units within the corresponding layer. So here the corresponding layer means the next layer. So in the next layer, after convolution or pooling operation, we generally generate the feature maps or convolved image. The next property is known as the shared weight. So shared weight means the filter that we use for convolution operation with the input image containing the weights or coefficient values. So these weights are learnable weight. That means we can learn these weights like weights and bias in the neural network through a number of iterations. That means the iterative process is initiated to learn these weights or coefficient values in the filter, and for every iteration we convolve the filter or window with the input image and generate the feature maps. And every time the fixed size of receptive fields are used to update these shared weights between convolutional layers and the pooling layers in the feature extraction part, and as well as the shared weights are also determined in the fully connected layer. So apart from shared weights, we can also determine the bias in the fully connected layer. So here the shared weights is an important property of the convolutional neural network. Another is the spatial subsampling. So spatial subsampling is obtained by pooling operation. So we will learn about the convolutional operation and pooling operation in the next slide. So this subsampling, through this subsampling, we can reduce the dimension of the feature map, which is obtained after each convolutional operation. And after convolution operation, generally we apply the pooling operation, and through pooling operation, we can subsampling the special image or the feature map, which is generated after each pooling operation. Now here, each neuron in CNN is responsible for a defined region of the input data. Okay, so each neuron means, if we consider each neuron corresponds to a pixel in the special region of the input image, then this each pixel within a CNN or convolved image or feature map is responsible for a defined region of the input data. That means if we initiate the first convolution operation, and before we get the feature map in the next layer, then each point, each pixel value or each point in the generated feature map is equivalent to a particular receptive field region or the neighborhood region in the input image. So this statement carry this information. So each neuron within a CNN is responsible for a defined region. Here the defined region means the region which is defined by this local receptive field. Okay. So this region may be 1 by 1 region. This region may be 2 by 2, 3 by 2, 3 by 3, 4 by 4, even 5 by 6, 7 by 7, 9 by 9. So like this region, and this enables this defined region will enable the neurons to learn the patterns such as lines, edges, and small details. So these lines, edges, and small details are found as the low-level features and mid-level features, as well as some features are found to be high-level features, and this will make up the image. Now, convolutional neural network is composed of the three layers. The first layer is called the convolutional layer, second layer is called the pooling layer, and third layer is called the fully connected layer. Okay. So convolutional layer and the pooling layer can be fine-tuned with respect to the hyperparameters. So in convolutional operation, the hyperparameters are the weights or coefficient values in the different filters of different various dimensions. Even in the pooling layers, we use different weights or coefficient values, and these weights and coefficient values in both the filters in the convolutional layers and filters in the pooling layers are known as the hyperparameters. Okay. Now, what is convolutional layer? Now, let us consider this is our input image, and this is the dimension of the filter. Now, what is filter? So, filter is represented by a receptive field, and this receptive field is defined within an input image. Okay. So, within the input image, the receptive field is defined as the neighborhood. So, this is the 3 by 3 filter, and this receptive area represents the filter, and the value of this, the weights of these filters may be externally represented or may be internally represented. When the weights of these filters are internally represented, that means they are using the pixels of the input image itself, or if these weights of the filters or the coefficient of the filters are externally defined or externally represented, then here we can use a randomly assigned values that are to be learnable or that are to be trained. So if I decide initially, if we decide the random values for these weights in the filter, then this filter will slide over this across this image. Okay, so if we if this sliding may be overlapping or sliding may be non-overlapping. Now, if we consider the sliding is non-overlapping, then here we can consider this area. Okay, this area, and the center of the filter will coincide with this pixel value. That means this area is defined as the receptive field, and the center of this receptive field will coincide with the center of the filter, or this filter is also called a window. Okay. Now we will take the sum of the product between the filter elements and the pixel values within this defined area in the input image. And for this center pixel value, we will get a new pixel value, which is called the transform value, or the transform value, which is the newly detected feature. So we can start from this point. So this center of the filter is coincide with this first pixel value in the top left corner, and then we get a defined area like this. Okay, so this area we will consider this area, and we will get the sum of the product between the filter elements, that is the weights, and the pixel values. Now you will ask the question, so what will be the pixel values of this outside of the boundary of these images? So you may ask, what will be the value of this? So in this case, we will apply the padding operation. So padding operation is nothing but adding zeros to the outside of the image boundary. So the length of the padding may be 1 pixel, length of the padding may be 2 pixels, length of the padding may be 3 pixels. So this filter will be sliding across the images, and the center of the filter will coincide with every pixel in the image, and we will continue this process. If this is non-overlapping, then we can initiate the filtering operation like this. This is the non-overlapping. Okay, non-overlapping filtering operation. So in this case, we will map these 9 pixel values to 1 pixel value. So in this way, we will get 2 by 2 feature map. That means after convolution operation, we will generate 2 by 2. That means the pixel values of this area will map to this pixel. Pixel values of this area in the input image will map to this pixel in the feature map. This area will map to these pixel values, and this area will map to this pixel value. This is for the non-overlapping. If we do not consider the padding, as well as if we do not consider the convolution will be non-overlapping. If the convolution is found to be overlapping, then we can get 1 pixel distance apart overlapping. We can get 2 pixels apart overlapping. We can get 3 pixels apart overlapping, like this. Okay. So in this case, here we can see that this is the input image, this is the filter, and this is the feature map. Okay, that means here in this case we have applied the overlapping pooling operation, overlapping convolution operation, and this filter is being found to be sliding as overlapping across the input image, and we have generated this feature map. This feature map is nothing but the convolved image. That means after convolution with the filter, after convolution of the input image with the filter, we have generated this feature map of the convolved image. So in this convolved image, we have generated 4 by 4 number of pixels. That means 16 pixels we have generated. So here input image is represented by I, and here F is the size of the filter, S is the size of the stride. Stride means that how many pixels we can consider for overlapping or non-overlapping. Okay, and the resulting output is represented by capital O. So here O represent the feature map or the convolved image. Now let us try to understand the filtering dynamics. So let us consider this is the input image. So this represents the input image, okay, and this is the x-axis, this is y-axis, and this is called the mask or the filter. So we are using 3x3 filters, and this filter is containing the weights. As I said, this element of the filters are called the weights or coefficient. So here the center of the filter is represented by W0, 0. Okay, and this corner top left corner weight value is represented by W of -1, -1. Okay, so that means here when we go top of this center weight value of this filter, then the x-axis becomes negative. Okay, x-axis become negatives, and when we go bottom to this bottom to this horizontal line, or bottom to this uh, center of the filter value, then we get the y value or x coordinate. X coordinate becomes positive. So at the bottom we get the x coordinate becomes positive. At the top we get x coordinate become negative. Similarly, if we go towards left to this center of the filter value, center of the filter, then we get the y coordinate to be negative, and on the right y coordinate to be positive. Okay. Now what we are doing, we are convolving this filter with the area decided by the receptive field in the input image. Okay. So this can be represented by this formulation. So this formulation represents the convolution operation. Okay. So in convolution operation, we consider the sum of product between the filter elements and the pixels which are defined within the neighborhood area represented by the receptive field. Okay, so this is the filtering dynamics. So once we understand the filtering dynamics, so it will be easy for us to understand the convolution operation in convolutional neural network. Next is the pooling layer. So the pooling layer here is pooling layer is used to downsample the input feature. Okay, so this input image is represented by 6x6 dimension, and this 6x6 dimension means we are having total 36 pixel values in this image. So this dimension of this input image is 6x6. Now when we generate the feature map, so this feature map becomes the dimension of 3x3. Okay. So that means when we apply the pooling layer, so pooling layer reduce the dimension of the input image or the feature map which is generated in the previous layer is reduced to the small image or the feature map in the next layer. Okay. So after convolutional layer, generally we apply the pooling layer, and the pooling layer is a downsampling operation. So this is applied after the convolutional layer, and this can do some special invariance. So special invariance means when we reduce the dimension of the feature map to a reduced dimension of the feature map, then the reduced dimension will contain all the properties of the previous feature map. Okay, so that is why this is called the invariance. This reduced dimension of reduced dimension of feature map versus the special invariance. Now, generally, we can apply two different pooling operations. One is called the max pooling, another is called the average pooling. So, in the max pooling, when we apply the max pooling, so if we apply the max pooling, then let us consider this is the 2 by 2 max pooling we are applying. So, this area will be defined by 2 by 2 neighborhood. So, in this neighborhood area, so there are 4 pixels. So, among these 4 pixels, we will pick up the pixel value which has the maximum level value, and this pixel value will be the neuron or the pixel value in the feature map in the next layer. Okay, and if we consider the average pooling, so average pooling will consider the average value of this neighborhood area. Okay, and this average value become the neuron or the pixel value in the feature map in the next layer. Okay, so this pooling operation can preserve the detected features, and here we can most of the time we apply the pooling operations, and in some times we can apply the average pooling. The next layer is known as the fully connected layer. So here the fully connected layer operates on a flattened input vector. So how could we get the flattened feature vector? So let us consider this is the feature map of the convolved image which is obtained after the last convolutional layer. So after last convolutional layer, we have applied pooling layer for one more time, and after applying pooling layer, we have generated this reduced size of the feature map, and this is the two-dimensional feature map. Now we have to transform, or we have to convert this two-dimensional feature map into one-dimensional feature vector. Okay, so how could you obtain this one-dimensional feature vector? So now for converting into one-dimensional feature vector, so we will consider each row in this feature vector, and the first row will be arranged in the first position. Then second row will append to the end of the first row, and third row will append to the end of the second row. So in this way, we can construct the one-dimensional feature vector. So this one-dimensional feature vector is fed to this fully connected layer, and fully connected layer may be a simple multi-layer perceptron, or a multi-layer perceptron which is having a number of hidden layers. That means more than one hidden layers we can use in that type of multi-layer perceptron. And when we fit this one-dimensional feature vector as flattened vector to this fully connected layer, then this the information containing by this one-dimensional feature of the flattened vector will be propagated across these hidden layers, and finally here we generate the output, and this output is compared with the ground truth. Ground truth means the actual output, and then the error is computed. And when the error is computed, we backpropagate this weight, we backpropagate this error and compute the gradient, and then again use that gradient in order to compute the weights. So here in this fully connected layer, initially we randomly assign the weights to the each connection between neurons in the hidden layers and the input layer and the hidden first hidden layers, and these weights are updated through an iterative process. Okay, and similarly here we also update the weight of these filters. Okay, weight of these filters also been updated through an iterative process. So these are called the model parameters. So initially we can assign the random values to these weights of the filters, as well as we can randomly assign the weights to this fully connected layer, each link to the fully connected layer. And when an error first time when an error is generated, this error is propagated through backpropagation mechanism or backpropagation network, and this error is used to compute the gradient, subsequently compute the weights, and these updated weights are used to initiate the second iteration, and this second iteration again generate the errors, and these errors are again compared with the ground truth of the actual output, and then again we compute the gradient and weight values, updated weight values, and generally we try to optimize the errors through this training process. And when we complete the training process, we will see that the error is found to be optimized, and error is found to be optimized, then we optimize the training error. So in this way we can train our model, entire convolutional neural network model. That means this entire model will be found to be trained during training. Now we can use any test image, and then this test image will use the updated weights in the filters, updated weights in the fully connected layers. And using these updated weights, the test image will generate some output, and this output will be compared with the actual output or the ground truth output. And then we can decide the belongingness of the test image to one of the classes. So this is the general working principle of the convolutional neural network. Now, what are the different hyperparameters we can obtain in the convolutional neural network? So the convolutional neural network, convolutional layers in the convolutional neural network will contain the filters for which it is important to know the meaning behind hyperparameters. So what will be the dimension of the filter? Now, if a filter of dimension f by s is applied, okay, if we apply f by f dimension filter to an input image containing C channels. C channels means for grayscale image C becomes 1, and for color image C becomes 3. So the dimension of the filter becomes f into C. Okay. So depending on the value of the C, the dimension of the filter becomes f into C. And if C is found to be 3, then this becomes the volume. And here we perform the convolution on an input image of dimension I into C. Okay. Now, if I is an image, if a single image is used for the training, then if a single image is used for the training and the value of C becomes 1, that means we are using grayscale image, then the dimension of the input image will be I into I. Okay, and dimension of the filter will be f into f. Now, if we are using n number of grayscale image in a batch, okay, grayscale image in a batch, then the dimension of input volume becomes I into n. Okay, since we are using n number of images, input images for training at a time, so therefore the input volume becomes I into n, and input volume and the filter volumes becomes f into n. Okay, that means n times we will apply this filter of dimension f into f to the input volume or the input image I into n. Okay, so other than C, if C is a color image, then this dimension becomes I into C into n. Okay, and dimension of the filter becomes f into C into n. Okay, and this will produce the feature map. So if this is the dimension of the input image, if this is the dimension of the filter, then the dimension of the feature map becomes O into O into 1. Okay, O into O into 1. Any questions? If you have any questions, you can ask me. Otherwise, we will continue this class in the discussion in the next class tomorrow. And tomorrow we will finish this topic. If you have any questions, you can ask me. Okay, that's all for today.